All right, welcome. Thanks for coming. My name is Frank, and I'm here to share with you a tool that I wrote called Link What You Include. And I hope to show you that you can use it to prevent architectural erosion by maintaining a coherent CMake target model. Before I get started, I'll tell you a little bit about myself. I work for Esri. We are a GIS company. That stands for Geographic Information Systems. It's basically geography on a computer. We've been in that industry for a long time. We have a lot of products and services. The product that I work on is a library, and it's very cross-platform. It's written in C++, and we try to keep up to date with the latest standards and the latest methodologies, practices, the latest tools. And one thing that I contributed to that is I'm the primary author of the CMake build system. I've been using CMake for a long time. One of my first jobs was in medical imaging, and I used ITK a lot. And if you don't know, that's where CMake got started. So I've been using CMake for a long time, and I've had the opportunity to rewrite existing build systems in CMake on 2 occasions. And if you've never done that, it's a unique experience. There's always a period of time where there's 2 build systems, the one that everybody uses and the one that everybody breaks all the time. And if you're like me, that gets annoying to fix all the time. But it's an interesting perspective on the changes that people are making. And you end up writing tools to help you maintain the build system. And those tools were kind of like the precursors of Link What You Include. So what is Link What You Include? So imagine at the end of this conference, you go home, you're back at your desk, and you're working on a change. You got your ID up, you're making changes, or maybe somebody else made a change and you're reviewing their code. This is a cartoon rendering of what a typical change might look like. We got your CMake file and we got your C++ file. And imagine these things are much bigger, there's a lot more code, and they're in a directory with a lot more files, with a lot more code, right? So what I'm showing here is a library, foo, and there's the CMake code that declares it and says that it links to these 2 other libraries, bar and baz. And then here's a source file that's using bar and baz. And suppose this change that you're working on or you're reviewing, you're removing this function that is using baz, right? So you're removing code that depends on some library. When you do that, you should remove the header that declares the thing that you're using, right? And you should also remove the library from CMake. Well, it shouldn't be too surprising that both of those changes aren't required. You could forget to remove the header. It's still going to compile, right? That's fine. And you can forget to remove the library. The CMake will happily put that library on the link command line, and your toolchain will happily ignore it. So that's kind of annoying. But suppose we successfully remove that, and 6 months later, we're working on a brand new change. We're going to introduce this brand new feature, and we're going to write this function that introduces this other dependency, baz, right? So when you add code that depends on some library, then you should obviously include the header that declares that function and add it to the CMake build system. Well, it might be surprising that both of those changes are also not required. No, they're not always required. Sometimes they're required. So that the header, that's probably not too surprising. We've been dealing with headers for a long time. If you forget to add that header, it might still compile because it could be that bar something.hpp is including some header, which is including some header, which is including baz, something awesome, right? So that header is already in our translation unit, and if we forget to add it here, which we should, it's still going to compile. Everything's fine. You may be more surprised, though, that we could forget to add the library to CMake, and I'm going to tell you more about that in just a little bit. So I've identified 2 problems: incoherent includes and incoherent library dependencies. So incoherent includes is when a file directly includes a header that it doesn't need, or a file doesn't include a header that it does need. And incoherent library dependencies is very similar. It's when a library or executable directly links to a library that it doesn't need, or doesn't directly link to a library that it does need, right? These are similar problems, and they lead to fragile code. And what I mean by that is, if you let this persist, someday you or somebody else is going to make a change in one location, and something very far away, unrelated, is going to break. And you're going to think, I didn't even know that existed. How does that happen? And that's annoying. That's frustrating. We don't like that. So the first problem, incoherent includes, there's a tool for that. It's called include what you use. It's been around for a while. It's good. It's not great, but it's a really hard problem, and it does a really good job. And so what it's doing is it's trying to enforce these two rules. It's scanning your code with a Clang-based view of everything, and it's finding the symbols, and what I mean by symbols is a type or a function, a variable or a macro, like anything with a name. It's finding those, where it's used and where it's declared, and then enforcing that if a symbol is declared, then it, if it's used, there it is, I was confused. Okay, so if the symbol is used in a file, then that symbol is declared either in the file, in its associated header, or in a header directly included by the file or its associated header. So associated header is, a CPP file often has a header that's associated, right? So that first rule is enforcing that if you use something, then you include it. You include what you use. The second rule is the converse, and that's actually probably more interesting. So if a file includes a header, then there is a symbol used in the file that is declared in the header. So that's saying if you use it, then you include it. Or if you include it, then you use it, right? Or don't include what you don't use. And it's interesting that that second rule is doesn't mention anything about the associated header. It's just a subtlety with the thing. This isn't a talk about include what you use, but I think it's important to like appreciate that this is a hard problem and there's some subtleties to it. There's a newer version of this. It's called include cleaner. It's not. It's an independent project. It came out of the Clang D project. I don't know its exact history, but there's a Clang tidy checker, and so it's trying to solve the same problem. Works probably very similarly, but they have maybe different emphasis on things. If you run these two tools, they're not always going to agree. But this one is worth keeping your eye on. I think it's very promising. So that's include what you use. The second problem, there's a tool for that. It's called link what you include, and here I am presenting it. So it's enforcing two rules. If a source file of target A, and by target I mean library executable, if a source file of target A includes a header of target B, then target A links to target B. That's if you include it, then you link it, link what you include. And the second rule is the converse, just like before. If target A links to target B, then there is a source file of target A that includes a header of target B. Okay? Now, this isn't quite stated precisely enough. I'll have a more precise version later on. But for now, this is basically what you need to think about. Now, this tool, I think, is very similar in some ways to other static analysis tools like Clang Tidy or include what you use, except it's different in an important way. So Clang Tidy is telling you that this expression is bug prone, or this file is doing something incorrect, right? And link what you include has got a bigger scope. It's telling you that this library is doing something incorrect. And so that gives it more of an architectural, it says something more about your architecture. And so I want to lay that out, that context, before I tell you exactly what it does and how it works. So we're going to start with what a modular architecture is. And then we're going to talk about the CMake target model, because you have to understand that in order to understand what the tool does. And it's also a really important concept. And while we're there, I'll show you why you don't necessarily have to have all your dependencies that you actually depend on listed in your CMake files. And then I'll show you how the tool actually works and how it can enforce a coherent target model. And then I'm going to talk about something else that's more grander, the a tidy dependency graph, and then we're going to wrap it all up. All right, does that all make sense? Everybody with me? All right.
Nothing wrong so far.
Thank you.
I'll let you know when I disagree.
I look forward to hearing your disagreements. All right, so a modular architecture. So back to basics, all right? A fundamental principle of software design is to take something large and complex and to decompose it into smaller, simpler modules. Right? When we do this well, it improves all kinds of things. It has a lot of qualities, right? It improves comprehensibility, development time, flexibility, testability. And the key concept is complexity encapsulation. What I mean by that is that we don't have to consider the complexity of the entire system. We can just focus on one thing at a time and only worry about the rest of the system and as far as it depends on it, right? So I've written the dependencies of A with double boxes, so that's to represent the interface of a module. Right? So inside, we don't have to know about its details. That complexity is hidden, but we just have to worry about its interface. And then the other things, I don't know if you can see them, right? But the rest of the system, you don't have to worry about it so much. Like maybe it affects you somehow, but like for the most part, you can ignore it. And that's hugely powerful. It helps you comprehend it because like you can understand the code in A really well and only worry about the interfaces, the other things, and not worry about everything else. So it makes it easier to understand. You can develop things faster because two people can work on independent libraries at the same time, and they're not going to be stomping on each other's toes. It's more flexible because you can make a drastic change to the internals of a library, and it's not going to affect the rest of your system. Or you can like build new libraries out of existing components, right? And it improves testability because you can instantiate one of these modules by itself and maybe mock out the other things, and you don't have to spin up the whole system in order to test it. So this is all good stuff, right? But notice I said when this is done well, we get all these qualities, right? So what does that mean? How is this done well? Well, we've been thinking about this for a long time. This is not new stuff, right? And a design principle that's often repeated is that modules should have high cohesion and low coupling. So high cohesion is when the code in the module is focused on a single responsibility. It does one thing and it does it well. And low coupling means that there's minimal dependencies between all the modules. Right? So I said this is not a new idea. There was a paper in the 70s that like talked about how to do this well, right? This is, I claim that this is kind of a solved problem. We know how to design good modular software, and everybody in this room probably knows it when they see it. And if given a brand new project, they could do some really great modular architecture. But I claim that this is really hard to maintain over time. Given a good architecture, how do you keep it good over 20 years? I think we don't talk about that enough. That's hard. And I think the reason is really simple. It's just the cards are stacked against us. It's relatively easy to add code, and it's relatively hard to change the architecture. It's not like it's impossible to change the architecture. It's just a lot harder than it is to just add code. And after 20 years of just making little tiny changes, we probably should have made some bigger architecture changes along the way, and it's just easy to lose sight of that. All right, so let me just dwell on this a little bit more. Let's look at cohesion over time. So here we're focused on the library E, right? We're not worried about the rest of the system. We're just thinking about E and its dependencies, which is only one in this case. And we're going to add some new code. We tend to add more code than we delete, right? And new code just inherently tends to decrease cohesion, right? I can't imagine adding code and make something more cohesive, right? It's just, at the very least, it's going to be as cohesive as it was. But over time, enough little changes, it's going to decrease cohesion. And so I'm going to represent that as it's going to get a little bit wider, right? Not deeper, it's going to get wider. And the cool thing about cohesion is that this is relatively easy to see because we can still maintain our little focused view on it and not worry about the rest of the system, right? It's an intrinsic property. We don't have to, we can just look at the code in the module by itself and determine whether it's cohesive or not. Okay. Now let's look at coupling. Similarly, new code tends to increase coupling. Right? You're not going to add code and remove a dependency. So over time, we're going to tend to add new dependencies, and coupling is just going to increase over time. But this is relatively hard to see because coupling is an extrinsic property. You can only assess coupling by looking at the entire system. We can't have our little focused view anymore. So this new dependency might seem reasonable when looking at it like this in isolation. It's just one dependency, right? But if you look at the whole system, it's actually an unreasonable dependency because we just introduced a circular dependency. And I don't know, this is a toy example, right? But the principle is what I'm getting at here. And so circular dependencies are bad. They're terrible. We don't like them. And the reason is because now any one of those modules in the circular dependency can't be used by itself. If you use one, you got to use them all. They're essentially a new module. And so I drew a box around it, right? We might as well make it one library because it's all connected, right? But now, by definition, it has low cohesion because those things were intended to be independent, right? So, and it was just so easy to just like this little change, and now suddenly our coupling is much, much worse, and it's really hard to see. Again, this is not a new issue, right? John Lakos has been talking about this forever. Here's a quote that I found. Achieving software designs that avoid cyclic physical dependencies among cohesive physical modules is arguably the single most important aspect of successful large-scale software design. That's a pretty bold statement. I'm not sure I'm willing to go that far, but I like the quote. We know these people, right? These are, oh, yeah.
What does physical mean in this context?
It means not logical. It means like a file or a library and not like a class or a function. Cyclic dependencies work against modularity and are the bane of large projects. Avoid them. Okay, I think I made my point, right? The main problem, I think, is that we can't see this dependency graph, right? It's not really written down in any one place. It's kind of an emergent property. We write our code and then we like make these links and then the dependency tree just kind of happens. But we've got something that's close, and that's the build system. So if we look at a CMake file that talks about this library A, you know, we add library and then we target link libraries to the dependencies, and that's like a fragment of our dependency graph. And so if we look at another CMake file, it's another fragment of our dependency graph. So it's tempting to think that we can just, in our head, merge all these CMake files together, and then there's our dependency graph, right? But the CMake target model has limitations. So if we go back to this library and we add a dependency, we should add it to the CMake target link libraries, right? But again, if we saw the whole system, we would see that this C dependency has a public dependency on libf. So that means the usage requirements for F are already attached to A. And so we actually don't need to write that. We should, but if we forget, it's still going to compile and everything's going to work just fine, right? So if we do our mental exercise of merging, oh yeah, target model need not be accurate. If we do our, oh, I blew it. If we do our target or our exercise of merging all of our CMake files in our head, and it might look like we have this dependency graph, but actually we have this dependency graph. That was the big reveal. So the point is that dependencies can be added and removed without updating the build system, and that's a problem. It's a hassle for build system maintenance. But I think the bigger thing is that it's weak visibility of this dependency graph. All right, so there's 2 times now where I've mentioned that the CMake files, the CMake logic doesn't have to be accurate, right? So let's see what that's all about. Any questions so far? Looking good, all right. So I think to really understand this limitation and also to really appreciate the beauty of the CMake target model, we need to see the underlying commands. And so I'm going to build up a really simple example from the ground up where I'm showing you the actual compile commands and link commands, and then I'll convert that to CMake, and we should be able to see what's going So I'm going to make a very simple prog executable. It's going to link to a static library foo. And this is going to be the way I'm going to lay out the source code. An important thing to note is that I'm going to separate the interface include files from everything else. So I've got this example foo include directory and example foo source directory. And this is a key technique. If you're not doing this, you should do this, right? You should separate your interface from everything else. And you should make the code that goes into this interface directory as small as possible, because we want to encapsulate as much complexity as we can, right? We want as small a surface area as possible. And notice the extra foo there, the example foo include foo, that's on purpose. We'll see why in just a second. Okay, so interface headers go here. Private source files, private headers go here. That's for the foo library. And then the prog source just doesn't have an interface, so it just has a source directory. All right, so to build the foo static library, these are the commands. I'm going to show you the commands for GCC or Clang, and I'm going to use bash. I don't have anything against MSVC or PowerShell or whatever. It's just this is better. So to build our static library, all we do is we compile each CPP file one at a time into object files. And each compiler invocation, we pass flags. And I'm showing this as a bash array just to make it easy to separate out. It'll be more clear later on when we just want to look at the flags. So what we're going to pass is an include directory. So this is telling the compiler how to find the include files. And so we're telling it, go search in the example foo include directory. That's where our interface headers are. And because of that extra foo there, we're forced to include a foo interface header with foo / something. And that just makes it nice to read. Okay, you don't have to do that, but I like it. That's the explanation for that extra foo directory. We're also going to pass the example foo directory, and this is where the private headers are, if we have any. And by doing it this way, we're forced to include it with a source at the beginning. And that makes it a little bit more distinct. So I like this convention. There's other conventions. It's not like this one's better than anything else, but I like it this way. Okay, and the last thing we do is we link all the object files together. It's pretty straightforward, right? Okay, now that we have the static library, let's build the prog executable. So very similarly, we're going to build all of prog's source files one at a time, and we're going to pass flags. And this time we're just going to include the interface directory for the foo static library because prog is going to use foo. I probably should have included an include directory for prog in case prog had public or had private headers, but it doesn't, so I don't know, I didn't do that. Okay, and it's important to note that when we're building when we were building the static library, I'm not including the path to the private headers of foo because that's private. We don't want to know about that stuff. Okay, and then similarly on the last line, we link all of our object files together, and but this time we also have to pass some arguments, and that's going to be the foo static library. So we link all the object files and the static library into our program. We're done. Okay, so if we remove all of the extraneous compiler commands, these are the flags that we're passing to the compiler to build the foo static library and the prog executable. And now let's do a thought experiment. What happens if we want to add a private dependency to foo? So like a source file, a private source file of foo is going to start depending on some other library bar. So what do we need to change to these commands? Well, we need to include the directory where the bar's interface headers are going to be, okay? But if we just do that, we're going to get a linker error because when we try to link when we try to link prog, foo will have unresolved symbols to this bar dependency, so we have to also pass bar to the prog link arguments. And this feels kind of unfortunate, right? Because prog doesn't know anything about bar. Prog just depends on foo. And foo depends on bar, but why do we need to know that internal detail? But we have to. Just like that's how it works. We have to know to put this there. And that's just kind of unfortunate. So to use foo, we need to know some of its implementation details. That kind of breaks this encapsulation of complexity. Okay, so let's continue. What if bar depended on, what if foo depended on bar, but publicly? You know, suppose one of the interface header files had a class and it had a private member that depended on this foo something. Bar something, excuse me. I'm going to keep messing that up, so Vito, keep me on my toes. Yeah, okay, prog depends on foo, foo depends on bar, and if foo had to include a public header of bar in one of the public headers of foo, then we're going to have to change something here, because because prog uses foo, it could be including the foo header that happens to include a bar header. So we need to tell prog about bar's include directory as well, right? And so not only does it need to know that foo depends on bar, it needs to know exactly how foo depends on bar. And this is not good. And now ask, like given this, right now we've built these commands, and all we've done is prog depends on foo, foo depends on bar. And now ask yourself, what if prog started using bar directly? What would we need to change?
Nothing.
Nothing. That's right. Nothing needs to change. We already have bar's interface include directory on the command line, and we already linked to bar. So we've got everything we need. So remember that. We're going to come back to that. You probably see where I'm going. But more interesting right now is what happens if bar has dependencies, right? Foo, prog, foo, bar. Well, bar could have dependencies too. What has to change? Well, we got to add that stuff there too. And if bar had transitive dependencies, I mean, like, okay, this is a nightmare. All right. And at first, when we first added this to the foo, we weren't too worried about it. But I don't know, that's kind of annoying too. Why should foo need to know where bar's interface header directory is, right? So all of these things that I've highlighted, this is all the stuff that you need in order for foo to use bar. Right? And that's a key insight. So the target model abstraction that CMake has takes this and runs with it. Right? So what is the target model abstraction? So you got a target as a library or executable or some other artifact, and each target has target properties. And this is an arbitrary key value pair that can be attached to the target. And I say arbitrary, and it literally means arbitrary. We can make up our own and put whatever we want in there. But there are some that are predefined and that have special semantics. And they're broken up into two groups: build specification and usage requirements. So the build specification is the set of things that you need in order to build the target. And the usage requirements are the set of things that you need in order to use the target. And they kind of mirror each other. So example properties are sources. For build specification, these are the things that you need to compile. The compile definitions, the -d flags to give to the preprocessor, the directories that we need to search for headers, and the libraries that we need to link to. That's all the stuff that we need to build. But when we're using it, there's going to be similar things too. Like in order to include headers, to use this library, you might need to have certain definitions to the preprocessor. So that's the interface compile definitions. And similarly for link, interface include directories and interface link libraries. Okay, this make sense? I need to be looking at somebody other than Vito because I know he gets it.
Me nodding my head means nothing.
Yeah. So the link libraries and the interface link libraries properties are special because they can reference other targets. And so this makes the targets form a directed graph. And this graph of targets along with their properties is the target model. I will mention there's two usages of the phrase target model, and I tend to use it both ways. And so it could be like the way CMake models targets and libraries and stuff. And it can also be a specific instance of that with like specific libraries, and I'm going to use it both ways. I don't know if one is better than the other, if I'm doing it wrong.
We normally
But-
use it to mean the abstraction itself,
Yeah.
but using it to refer to a specific instantiation of the abstraction is not considered a faux pas. People do it often enough.
Yeah. So I'm aware of that, and I'm committed to it now. So so I don't know. Just acknowledge. I want to acknowledge that distinction, and it's a convenient way of describing this stuff. Okay, so the essence of modern CMake is to declare targets and set build specifications and usage requirements on them, right? Declare targets. It's very declarative. And then given that, CMake will generate the low-level rules to build each target using its build specification in combination with usage requirements propagated down the graph from its dependencies. So like we set up this target model, and then CMake goes to town and does all of the stuff that it needs to, and we don't have to worry about a lot of it. It's a really great abstraction. So I showed you the low-level target properties. The way you normally interact with the target model is through target commands. These are target compile definitions, target include directories, target link libraries, and there's others. And they can set one or both of a corresponding property. So the target include directories can set the include directories build specification or the interface include directories usage requirement, or both, depending on a scope, right? So the scope is interface, private, or public. So if it's interface scope, it means you only want to set the usage requirement. If it's a private scope, you only want to set the build specification, and if it's public, you want to set both. So for example, for target include directories, if we're going to attach this to the foo static library, we might pass the example foo include interface include directory as a public dependency, which means that you need it in order to build foo, and you also need it in order to use foo. But the example foo directory is private. You only need that to build foo. You don't need it to use foo, right? So that maps to these set property commands, right? So the public include directory shows up in both places, and the private is just in the build specification. Okay, so if we go back to our example and convert it to CMake, this is the commands that we had to build the static library. And if we write it in CMake, it's going to look kind of like this. I'm going to show you a better version a little bit later on, but we're going to go with this for now. So you add library foo, that declares the foo target, and then you have the source files that adds these source files to the sources property. And then we target include directories. See, actually, I have highlights for this. Yeah, so we add the source files. That's where they were, and that's where they go. And to the target include directories, we're going to pass the public include directory, the interface include directory as a public scope, and the private as a private scope. All right, pretty straightforward, right? The prog executable, these were the commands that we had before, and we convert that to CMake in a very similar way. We're going to add executable to declare the prog executable, and we're going to give it the source files. And then we're just going to say prog depends on foo. We're done. We don't have to tell it anything else. CMake does the rest, right? It's pretty cool. Now, if we go back to our extension, right? So this is what we have now for our CMake, and we're going to imagine adding a private dependency to foo, right? So in that case, remember what we had to do before? We had to tell prog about the foo static library, but here all we have to do is target link libraries foo private bar, right? We just say foo depends on bar, and we're done. We just need to add the dependency, right? And if we're going to do the public dependency, all we have to do is just change that private to public. It's now a public dependency. That's all we have to do. CMake does the rest. It's fantastic. And if bar has dependencies, nothing has to change. If bar has transitive dependencies, nothing has to change. Like that complexity is now encapsulated. We don't have to see it anymore. But what if prog started directly using bar? Remember how I highlighted that earlier on? Nothing has to change.
You
So-
make it sound like such a bad thing when you put it that way.
Well, yeah,
Yes.
I mean, it is kind of a bad thing. I really don't like it. But I really do like the target model. So I'm not trying to diss it in any way. What I'm trying to do is enhance it, right? So I'm gonna plug this hole, and everybody wins. So the CMake target model of modern CMake is a concise and powerful way to organize a project's build system. It hides low-level toolchain details behind this higher-level abstraction. It simplifies the build specification by mirroring a project's physical dependencies, right? But this is a leaky abstraction, and the reflection of this physical dependencies need not be accurate. And so I want to plug that leak. Okay, so we now have enough language about what the CMake target model is that I can now describe what leak what you include does. And that's what we'll do next. All right, so the base assumption is that we are include what you use clean. So this is, I showed the rules, I showed this earlier, so I'm not going to go over it again. But I wanted to put it on the slide because I want to make the corollary of this, and that if a file uses a library, a file uses a library if and only if it includes one of its interface headers. So if we're include what you use clean, then that is a true statement. We're not always include what you use clean, so we can't always say that, but I'm just gonna assume that that is a fair statement, right? And we can still get a lot of value out of what follows, but it might not be like perfectly accurate unless we can make this claim that I've called this corollary here. Okay, so with that, I can define what link what you include clean means. And so this is the more precise version of what I showed earlier. So there's two things. Target A lists target B in its interface link libraries property if and only if an interface header of target A includes an interface header of target B. So that's building right off of that corollary, right? If we're including a header, then we need to link to it, right? And that's on the interface side, right? The private side, the build specification side, is a little bit more complicated. Target A lists target B in its link libraries property if and only if a private source file or a private header file of A includes an interface header of target B, or includes an interface header of target A itself, which in turn includes an interface header of target B. So that second bullet point is kind of a subtlety that in earlier versions of this link which you include that I've written, this is like the third version I've written, I didn't appreciate this subtlety. All right, so I'm on slide 43, and now I'm going to finally show you how to use this tool. I'm not sure if I mentioned it, but it's open source. It's on GitHub. You pull it
Can
down.
you go back? I just want to parse that second
Sure.
point.
Yeah.
It includes an interface header of target A that includes an interface header of target B. Okay, listen to that.
So that means if we're building a source file,
Yes.
a private source file, and it includes an interface header, which includes the dependency, we need to have that dependency
Okay. Yes.
as a private.
Yep, makes sense.
Yeah.
So earlier you were saying there's three categories: public, private, interface.
Yep.
So interface link libraries, obvious to me where that belongs. Link libraries was public?
Yeah, so link libraries is private. So if you're private, you only have it in the link libraries. If you're interface, you only have it in the interface. And if you're public, it's in both.
Okay.
And so the link which you include tool operates at this lower level where there's only these two properties, but you want to think about it in terms of the scope, which is three properties. So it makes it a little confusing. Yeah, that makes sense? Okay. Good?
Second bullet point still screwing you up a little bit. If it's a private source of target A, how is it including an interface header of target A? Because nominally the private sources of A don't have access to the interface headers of A unless they are also private headers of A.
No. So static library A
Yeah.
has a class, right?
Yeah.
That happens to be a public in the public interface. So
Yep.
it's declared in an interface header of A, and its source file is private.
Yes.
So the source file has to include the interface header.
Okay, but then that's not, so I have two sets of headers, right? I have my interface include directories, and I have my include directories, the private include directories. I have two,
Yep.
I have two include directory
Yep.
properties.
Mhm.
The only things that my private sources can see are things that are in my include directories or in one of my dependencies interface include directories.
Yeah, so I'm talking about my interface.
I can't
dependency.
see my own interface, is my point. I can
Why-
only see my private.
Why can't you see your own interface?
Because the interface is a usage requirement, it's not a build requirement. When I'm building my sources, I only use my private include directories.
Yeah, okay, but so if the interface include directory is public,
Yes.
then that directory is going to show up in the
In
interface
both, yeah.
and in the link
Yes.
libraries. So maybe the problem is I'm conflating interface include directory, or
Interface header, interface include directory, same thing, yeah.
yeah, but so I've got this interface header of A
Yeah.
that a private source file is including.
Which means that
Right.
the actual include directory that the header appears in is actually it was listed as target include directories public.
Right.
So it appeared in both properties.
Yeah.
Okay,
exactly.
there we go. That makes it, okay, I'm there.
Yeah, yeah.
Lowercase versus uppercase interface?
Yes, lowercase versus uppercase interface is a good way to put it.
Okay. You're good. What, yeah.
Why didn't you include interface headers of target A that include an interface header of target B?
That's rule 1. The second line of rule 1. Interface headers of target A includes an interface header of target B.
Oh, okay. The logic here is.
Thinking about graphs is hard when you're thinking about them in English.
Yeah. Yeah. I spent a lot of time getting this language. Right? I went through multiple versions. And a big step for me was the if and only if, because it used to be, so when I said the rules for include what you use, I couldn't do the if and only if. I had to do if then and then another if then to do the other direction. But it just works out that we can state this as implications, as equivalencies, I mean. Okay, we good to go?
Yes.
All right, so to use link what you include, go get the code from GitHub, and it comes with a CMake module. And so in your CMake logic, you got to include that, and then that defines a CMake function called link what you include, and you call that function for every target that you care about. Right? So every target that you want to participate in link what you include, and that means you want it to check that it links what it includes, and you also want other things to check that it links that if it includes it. Right? So it's like this closed set of things. Everything else that's not called, that we don't pass to link what you include, is ignored. And so like basically you want to call this on as many things as you want, as you can. And then optionally you can provide an include prefix. And so what that is if you tend to include an interface header of something with a prefix directory, you can tell link what you include about that. I'm going to talk more about that later. But for third parties, if you can, you kind of probably should, especially if you're an open source project. But I'll talk more about that in a little bit. Okay, and as an aside, if it's annoying to call this function on every target, this is how you could just do it for all targets all at once. I'm not going to go through this. It's just like a CMake trick that's on the slide. I can see you guys are reading it, right? But so basically, just look at the second part down here. Get all targets, and then for each target, call link what you include on it. You might not want to do this because there might be a target that you just don't want to participate, and you want to like opt out. But if you did, this is what you do. Okay, so you guys can look at that later and tell me if I got it wrong. So now that we've added link what you include support to the build system, now we run link what you include. And so what you got to do is you got to configure CMake with a single config generator. Sorry. And you have to set export compile commands to on, right? Because link what you include is Clang based, and so we need the compilation database. And then you invoke link what you include. I call it LWI just because. And you give it the path to the build directory so that it can find the compilation database. And you can give it an optional set of targets. So if that -t, it will take any number of targets, and you can leave it off if you want to, in which case it'll run it on all targets, right? And then it's going to go and do its thing, and it'll generate errors that look like this. lib-a does not link to lib-f, but it is included with private scope. And then for some of the errors, it'll tell you the header that it found that it was including. So here it found that this some interface header of lib-f is included from a private source file of lib-a, line 17. That's neat. In general, all of the errors look like this. And it's going to say that target A is linking or not linking to target B with some scope, but it's included with some other scope, or it's not included or something, right? That's all the possible errors. Okay, how does this work? So link what you include does the following. It does three things. It has to acquire the build system-based dependency tree. And for that, I have a machine. We need some way to read the target model, get it from CMake somehow, and read it. And so that we've got the build system-based dependency tree, and then we need to compute the include-based dependency tree. So we're going to go scan the source code, find the includes, map those headers to their corresponding targets, and now we have the include-based dependency tree. And once we have those two trees, they should be equivalent. So we just compare the two and report diagnostics. It's really actually not that complicated. So for the machine-readable target model, the ultimate goal is to use CPS. CPS stands for Common Package Specification. It's a way of, it's an emerging standard that describes for a software package that's on your file system, here's how you use it. Here, if you're a build system or you're a package manager or something, this is how you use this thing, right? And that's like the target model, right? And so ultimately I want to be able to just read this. That's my machine readable target model. It's not quite there yet. It's possible to use now for, theoretically for some things, but the requirement would be that the interface include directories for everything that's described by CPS have to have just disjoint directories. I'm going to talk more about that later. But for a complete solution to use CPS and not depend on CMake at all, we need these two things. We need build systems that can generate CPS files for all built artifacts, including things that aren't installed, right? So I'm using this at Esri, and the product that we have, it's one big shared library, but it's decomposed into a bunch of static libraries. And we install the shared library, but I care about the static libraries, right? I know that's on the radar, and I don't know. I hacked on CMake a little bit to try to get that to work, but I don't know. Someday, maybe, I'll get there. But so I'm not asking you guys to do this for me. I'm like, I can make a pull request, I know, but I'm just listing this is what needs to happen.
For the audience at home, half the people at this talk are CMake developers.
Right. And the other thing I need is for CPS to support interface manifests. And so that's, like for this library, this is the list of header files, right? That's the ideal solution, right? And that's on the CPS radar, right? So when this project was announced, or I don't know, in 2023, Bill and Brett gave a talk kind of describing this CPS project and what it was all about. And towards the end, Bill was listing the future goals. And one of them there you can see is explicit manifests of headers and modules. And the reason was for link what you use tooling, right? But when Bill was talking, he actually said link what you include, right? Because you're a smart guy, right? Link what you use is really hard, but we're going to let include what you use do that. It's link what you include is the easier problem. Okay, so, the other thing I wanted to mention here is that this is not like my snowflake idea, right? Other people have had this idea, right? So I don't want to claim that I'm a unicorn. Okay, so until we have CPS, we still need a machine readable target model. And so in the meantime, we can get by with an CMake specific ad hoc solution. And that's what this link what you include.cmake thing provides. And so by calling link what you include the CMake function for every target, there's some wizardry underneath the hood that's generating a JSON file with a list of targets and a bunch of their properties that we need, like the link libraries and the interface link libraries, the source files, and some other things like interface include directories and this header set thing, which I'll talk more about. You know, it's ironic that in order to describe how this works, I couldn't figure out a linear path. Like everything sort of depended on itself. It's like kind of like a circular dependency. Yeah, and I also inject information into this target model. These include prefixes that I mentioned about. I'm sort of like adding that to the target model, and that's getting written out there too. I'll explain more about that again later. Okay, so how does that actually work? I'll show you a little bit of code. So it's tempting to think that this function can just do this. Hey, CMake, give me the link libraries property, and I'm just going to like write it to a JSON file, right?
If only.
It doesn't work that way. And that's because, in general, these properties can include generator expressions. And so what that means is that many things in this list might not be known until generate time. And this code that you're seeing here is executed at configure time. So CMake has phases, does a configure phase, and then it has a generate phase. And some things we don't know until we're generating the build system. So the classic example is something that depends on your build configuration, whether it's debug or release or whatever. And it's perfectly reasonable to link to something in debug and not link to something in release, right? So it gets more complicated. So instead of doing this, we got to do something more like this. So give me the link libraries property, and then I'm going to start wrapping it in an ever expanding generator expression. So I don't really want to go through this. I just kind of wanted to show that there's some wizardry under the hood,
I
right?
just wanted to demonstrate that someone is using target GenX eval.
Yeah. So target GenX eval. So these properties, when they're expanded, they might depend on the target, and so you got to tell that. I normalize the path, and like the rest of the stuff is just generating something that looks like JSON, right? So the output of that is a little JSON snippet. So that's how that works. It's more complicated in each property. Some of them have like special cases that I got to worry about and whatnot, but that's that. Okay, so that's the machine readable target model. The next thing we need to do is to scan the source files and collect includes. Now I think this is the most interesting part. So I'm using Clang libtooling to write our own preprocessor. Libtooling is like the Clang compiler as a library, and so you can just do all the things that the compiler does. And that means I can be really accurate, right? I've got the compile commands, so I know what preprocessor flags are on, so I can ignore the headers that are being ignored by the preprocessor, and I can fall a step into the includes and like walk the entire include tree. And when I see an include declaration, I can get the full path to the include. This is all really great stuff. And because we're scanning all the targets, all the files in the sources property, and then checking that they're in the compilation database, we're like ignoring the private headers. That's an important thing to note. And yeah, we have the full path. So we crawl we scan all the sources and we crawl the include directory tree, and then we mark these includes as interface private or public, depending on the history of the processed files. So if we're processing a private source and then we include an external header, well, that external header is a private dependency. If we're scanning a private source and then we step into a private header and then we include an external header, that's also a private dependency. If we're scanning a private source and then we step into an interface header, which includes an external header, that's a public dependency, right? But so then you see, like, we're always starting with a private source. How do we get an interface dependency? We'll come back to that. It's just, I couldn't figure out a straight path. All right, so the first thing I want to talk about is, like, once we get these external headers, how do we map them to targets? Okay, so the best way is only possible if the targets know about their interface headers. So I mentioned earlier when I was showing you the CMake, I was doing it like this, and I mentioned there's a better way, right? No, I don't think anybody does it like this anymore, right? Because if you do it like this,
Nobody's a strong word. We wish nobody did it like this.
yeah, so nobody that uses Visual Studio does it like this. If you're using some IDE and you do it like this, your IDE is not going to know about your header files. Like you're going to have your project tree, and it's just going to have the CPP files. And I don't know, that's going to be annoying. You're going to like do a Google search, how do I fix this? And they're going to tell you, oh, you got to put the headers in the sources as well. So I think probably most people do it like this. And that's kind of weird that you're passing these headers to your sources property. They're not sources. You're not compiling them. You're just telling CMake about it so CMake can stick it into the IDE. And we also have these include directories down here, but these two things are kind of related, right? And so the modern new way of doing it is like this, right? So we just add library and we don't do anything else. We just declare that this is a library, and then we call this target sources function, and all the sources go in here. And notice we don't have the target include directories anymore because we specify that with the base dirs. So what I'm doing is I'm declaring two header sets, interface header set and private header set, and I'm telling CMake where, like, here's the list of all the files, all the headers, and here's their base dirs. This is like the include directories. And then the last section there those are the private source files. So now CMake has a lot more information about our headers. It can still generate the nice looking Visual Studio, but it can also have in the target model the list of the headers, right? And the link which you include function can see this and write it out. And so now I know about them. So by using this, link which you include can extract this exact set of interface headers for each target, and that makes mapping a header to the corresponding target trivial. I just go and find out which one it belongs to, and now I'm done, right? The other thing that this provides is that we can set this CMake feature, verify interface header sets. Now this is nice. So what this does, since CMake knows about your interface headers, it can generate source files that just include that like one header at a time, and then generate a target that builds these things as an object library, so it's not linking to anything, and it like does all of the right things like linking to the library so we get the usage requirements and turning off your precompiled header if you're using it. And so it's just building these headers in isolation. And that's kind of like making sure that they include what they use, right? Which is great. That's great, right? But what it's not doing is that it's not testing that you don't include what you don't use. So we still need to include what you use, but this is still great. It's useful for lots of things. In particular, it's useful for running Clang tooling on your headers. If you've ever tried to run Clang tidy on an interface or on a header-only library, right? That's kind of awkward. This makes it a lot easier. Yeah.
It also doesn't confirm that you're directly including what you directly use.
Yeah,
So-
you can still
Right.
have,
You can use bar things even though you only included through the thing.
That's a good point. Thank you. Yeah.
So it gives about a third of the problem, but it's still a lot
Yeah.
better than zero.
It's a smoke test.
Yeah.
Yeah. Right.
It does catch a lot of bugs, so I recommend it.
Yeah.
And the
Thank
Clang
you.
tooling point is important because you'll find that Clang tooling has to make a lot of heuristics to figure out what options are going to what header file. And when they have a single source file that they can look at that just has
Yeah.
that header file in it, a lot of analysis becomes easier for the Clang tooling.
Yeah. So I don't like that.
Oh, really? Never mind.
Yeah. So I'm avoiding that.
Okay,
but,
never mind then.
But yeah, I mean,
Pretend I didn't say it.
I don't know. I don't know. It's not like I don't like it. That's fine. I like Clang tidy and I want it to do that, but I'd rather like have more direct. Like, this is exactly what I need in order to compile this header. So yeah, okay. I'll get back to that in just a second. Right. So for this talk, the important thing with verify interface header sets is that link what you include can see these generated source files in this generated target and add it to this JSON file, and then the link what you include tool can scan these files. So that's how I can. So when I showed you that I'm scanning something to get an interface header, like I'm scanning the CMake generated source file, and then I'm like, that's not a part of any target that I care about, and so I'm just like in no man's land. And then now I'm in an interface header, and so when that's how I get an interface dependency. That was kind of subtle. Does that all make sense? Okay. All right, so what if you don't have a header manifest? What if you're not using the file sets, or like you're importing a target that doesn't know anything about its headers, right? We still need to do something, right? And the only thing to do is to match the full path of the header against the interface include directories that are on that target. And that works great if the interface include directories are disjoint, right? But that's not often the case for third-party libraries. So, like for example, I showed this earlier. So link which you include itself depends on the FMT library and TL expected. And if I install those dependencies in independent prefixes, you set the installation prefix. If you give those different directories, it might look like this, right? So say I'm installing into opt frank, and I'm going to install FMT into opt frank FMT. Then its interface include directory is going to be opt frank FMT include. And I'll install expected into opt frank expected, and then its interface directory will be in opt frank expected include. It's separate, right? So when I'm scanning the code and I see FMT include FMT core, it maps to this full path, and similarly for expected, and I can split that out on the interface include directories, and they're disjoint. I know which header or which target these things belong to, no problem, right? But that's not the only way to install things. You can install them into the same prefix, and this is the default, right? Just go into user local include, and then when I'm scanning there, and I split out based on the interface include directories, I get the same directory. I can't distinguish which target these headers belong to, but they're still distinct directories because they have this convention where you always include the FMT header with FMT/. It actually is disjoint. It's just that the part that makes it disjoint is spelled in the include directive, not in the interface include directories. So I need to add that extra part, and that's why I'm encouraging you to pass this to the link which you include CMake function to add that to the target model, so that I can disambiguate this situation. So this isn't a problem for link which you include.
But if you had a full manifest for the dependencies, you wouldn't need that.
Exactly.
Okay.
Yeah. So in the future, when CPS supports interface manifest and everybody supports CPS and does that, I don't have to do any of this stuff,
Okay,
right?
that makes
Yeah.
sense.
And then it's perfect, right? Because some libraries don't have this convention of always including with a directory. And if you put that in the same directory as another one that does it, we're screwed. You can't do anything. We just can't tell them apart. And
all the standard OS headers are
Yeah, just zlib.h and everything else are in one bucket. Yeah.
And so for that, my answer is just ignore those ones. Just leave that out of link which you include for now, or install them yourself into its own directory, right?
Write a CPS file.
Like if you use Conan, for instance, Conan puts everything in its own directory, and so that's not a problem.
Someday we can write a CPS file that says zlib goes to.
That has a full manifest, and then all this goes away.
Exactly. Yeah, the full manifest is the way to go. And this is kind of like, in the meantime, I could do some tricks, right? Okay.
Until reflection.
So now we kind of know more about how it works, right? We're getting these two dependency trees. We're getting the machine readable target model with all the CMake wizardry. We're scanning with the Cling tooling and mapping and getting our diagnostics. Okay, so in summary, in order to use link which you include, you got to include link which you include.cmake. You got to call this function on most of your targets, including imported targets. You should use file set. That's like the new cool thing to do. Specify your interface headers as a file set, right? Or if you can't do that, lay out your files such that your libraries have disjoint interface directories. If you can't do that, use include prefixes. If you can't do that, I can't help you. Use a single config generator. So that's not a hard requirement, but you're going to want to do that I mean, well, it is a hard requirement.
It's not
I can-
structural. It's
I
just
can-
you didn't
I-
implement the, yeah.
I could remove that, but you want to do it this way. So I was going to mention this earlier. The reason for that is because if you have a multi-config generator, the compilation database will include every file 4 times for one for each configuration, and then when you scanning that file, you got to scan it 4 times, and that's so now everything's 4 times slower. And I don't know, just do a single config; it's easier. Okay, yeah, you got to set export compile commands. Set verify interface header sets, and then run link which you include for every change and have 0 tolerance for errors. That's my summary. And if you do all that, the results are that when you change the dependency tree, you're going to be required to change the target model. There's no more accidental dependencies, right? And that means a less fragile build system and a more visible dependency graph. Yeah.
So since you're like sort of hard coding this into the CMake build system, is it gonna run all the time, or does it like do a no op when it doesn't have the Clang tooling around to run it? Or so I'm imagining I've got some project and I probably only need to do this when like,
In CI.
in CI.
Mm-hmm.
But this stuff is all over my CMake code now. How do I, and most of my developers may not have this tooling installed, how do they, or do they? Or how do you imagine using it? How are you?
Yeah. Everybody has it installed. that's how I'm using it. But you have to choose to run it. So it's not like part of the build. It's more like So I'm what is it like? Yeah. It's like run. Yeah. It's not like that either. So like include what you use or clang tidy. Like you can run those as part of the CMake build. I don't have that wired up. This is more like you can build, or you can run link what you include. It's like a separate step, and
Okay,
So the output of the CMake commands is a JSON file in the build tree, and then include what you use can consume that JSON post the configuration stage.
yes.
I
But you said
think Bill's just suggesting you can make a CMake cache variable that short circuits the whole include, and maybe it's
But
maybe it marginally speeds up your build and production work.
But all he's doing at configuration time is generating a JSON. He's not doing anything at build time. There's nothing to short circuit around. Am I
Yeah.
correct?
yeah.
No, you just get that too. It's just like return, if the cache variable set return nothing.
Yeah, but there's not a tooling mismatch. There's not like some binary that we expect to have in path just to generate the JSON.
Oh, you're right. It's not about incorrect builds. It's just about like, I don't want to run a bunch of procedural CMake.
Yeah.
I don't need, right.
Yeah.
It's not a hard feature that.
So if you just want to run link what you include, it's kind of annoying because you got to do a configuration,
Yeah.
and so I don't know, that
That's
is
true for
what it
clang
is.
tidy.
But usually we're building anyways. So we configure and then we do a build, and then we run link what you include because it's all there. Did that answer your question?
Yeah.
Okay. All right. So now let's move on. So like so far, how am I doing for time?
Yeah, you're about 20 minutes.
Okay, I think I'm doing okay. Might have to speed up a little bit. So this enforcement of a coherent target model is nice. Those things I just mentioned were good, right? But it doesn't really address like the big architecture problem I was spelling out at the beginning, right? Because link what you include could say, oh, you actually accidentally started depending on this thing, and then okay, fine, I'll just add it to the CMake. Like, that's fine, right? It like gives you the opportunity to think more about the dependencies, right? But it's still like, I don't know, I think we could do better, right? And that's because we have a machine readable dependency graph. We can do better. We don't have to just enforce that the target model is coherent. Like we can, the dependency graph is in CMake or in C++ code, and I'm a C++ programmer, right? Let's go after this coupling problem, right? And so to that end, I'm going to try, so I've added this feature to let's have 0 tolerance for cyclic dependencies, right? We can remove them, like we can just make them impossible, right? And let me show you what I did. So here's the help page for link what you include, and I added this tool option here, and so I modeled this, I stole this idea from the Ninja build system, they have this tool thing where it's almost like a whole other executable, but it's like this convenient place where they can just stick cool things in. And so I'm using it, I'm saying like, this is where I'm going to put undocumented features, right? But I'm going to tell you about one of them right now. So I'm documenting it. It's called tidy, the tool. And so you invoke what you include, just like you did before. Give it the path to your build directory. You can optionally give it a set of targets, but then you say tool tidy, and that tool takes a configuration file. And so what this does is it loads the target model as before, but then rather than scanning all the source files and doing the include mapping and all that stuff, it just runs checks on the dependency tree. And I've added 2 checks so far. I think there might be more in the future. They're called allowed clusters and forbidden dependencies. And both of these checks read the configuration file. So allowed clusters runs Tarjan's algorithm to compute the strongly connected components of the dependency graph. So what that means is the dependency graph is a directed graph, right? And a strongly connected component is a subgraph that is strongly connected. And what that means is any 2 nodes in the subgraph, there's a path that connects one to the other. So I mean, that's just like the graph theoretic way of saying a cyclic dependency. And there's an algorithm to compute it. And so now we can compute this, right? So what this tool does is it computes that, and then it compares the strongly connected components, the non-trivial strongly connected components, to a known set that's listed in the configuration file. So if the configuration file is empty, then it says you cannot have cyclic dependencies. But most projects that have been around for a long time might have some cyclic dependencies, maybe a few. And so if you're in that situation, what you can do is just document our existing cyclic dependencies in this file. And now this tool will generate an error if any of those cyclic dependencies increases in size, if any of the strongly connected components increases in size, right? So now it can't get any worse, right? And if you happen to remove one, it's going to give you a warning because it's going to say, hey, you should change your configuration file. It's now better than it was. So this is a snippet of what the configuration file might look like. It's JSON, and it's an array of arrays. So there can be more than one strongly connected component. Okay, and the other one is much more simpler. It's just going to check for the existence of specific dependencies listed in the configuration, and error if they exist. So my vision for this is that it might be hard to remove a library from a strongly connected component because there might be like 6 dependencies that you have to break, and you can't do it all at once. So you're gonna break one and then break another one, and each time you do the change to break a dependency, you can just add it to this list. Like, I worked hard to make that dependency go away. Do not add it back. Okay, so with these 2 tools, we can take control of our architectural evolution, right? So step 1 is to stop the bleeding. We document our cyclic dependencies in the allowed clusters, and then we refrain from adding more to that cluster, right? So that's going to prevent us from just accidentally increasing the size of a cluster. And then step 2 is the fun part. Break the dependencies. We'll make a change that breaks the dependency, and if we can remove it from the cluster, then great, update the cluster. If we can't, document the broken dependency and then repeat, right? And so now we have a path to make our architecture better. And now I suspect that there's other graph algorithms that can be added. Any ideas?
I haven't had a lot of some of these we can run right on the CPS files, by the way, so they don't necessarily have to be tied to include use. But I don't object to adding them to include what you.
Yeah,
Include, sorry.
I was going to mention that the reason I added that as undocumented is because I'm not convinced that it should be part of link what you include. Right. It's really something else, and so I'd be okay with like this idea going into like CPS config or some other tool or something. But yeah.
So like collisions and header include targets would be something you'd want to warn about. Like if 2 things in 2 different libraries both had tlexpected.hpp, that would be a thing you would want to flag and say, hey, wait a second.
Oh, yeah.
Like that, and that's actually a hole in the algorithm because there's not a good way to deal with it. Is like, well, which one did you mean? There's 2, right? And like you're probably the right thing to do is pick the one that Kling would pick. Is probably what your tool is doing. But
yeah.
like you should tell the user, by the way, you have 2 versions of TL expected in your graph.
Mm-hmm.
Now, why would that happen? Well, because somebody copied TL expected that. They should ship that. They shouldn't do that, and they should get it. They should. Some tool should say no, bad engineer, don't do that, right? That happens a lot with like JSON, right? Because these header-only libraries, people just copy them around, right? So, and again, you might still need the suppressions because you're doing a local development workflow, and it's okay in that circumstance because you're actually editing TL expected for reasons or something. But
so I like that idea, but that seems like that doesn't fit for this tool because it's like it's operating at the file level, and this is more like at the library level.
Well, it is at the library level because it's saying you as a library have. It's kind of in the conceit that you had used for the prefixes for the include targets. Like they all kind of fit together. They go together. They go with this library. So if someone reaches into someone else's space and messes around with it, they're going outside of their domain across the graph, and that's the problem. Does that make sense?
I'm not sure, but yeah.
I mean, it's literally like the use case is literally this happens. People copy like Enloma JSON into their package, and then it ends up on the search path too. And then you have to say like, well, which of the Enloma JSONs was the right one? And that's something link what you include needs to deal with on some level. It might be implicitly happening by the virtue of your algorithm, but like you can do a lookup to say where do I get Enloma JSON? It might come back with more than one library. And those cases are a problem, and the user should think about it.
Okay, all right, yeah. I think I get what you're saying now.
Yeah.
And that relates to something I was going to mention
Yeah.
later on, maybe, I don't know.
Right.
But yeah, okay, it's documented now, so I'm gonna think about that.
There's so many things that just like reduce to like problems that an engineer could describe, but they end up just reducing to either forbidden dependencies or cycles. Like, so can we go back to the forbidden dependencies? Yeah. So check for dependencies with some configuration error if they exist in the target model. So the list is a set of dependencies that lib e is not allowed to depend on, or it's a set of exceptions that are allowed to have lib e.
I should have mentioned that. Yeah. So this means lib e cannot depend on lib a directly. It's allowed to depend on something which depends on something which depends on lib a.
Yeah. So like the common thing that we see is someone has deprecated a library, right? And what they want to establish is at this point of deprecation, we have this many people who have this dependency. Like this dependency occurs this many times in a given graph, or appears at this many roots in the graph. And we never want that number to go up. We never want anyone to, like, this set of users is allowed to depend directly on the dependency, but no one else is for the rest of time.
Okay.
And so that sort of thing is like very useful because what it allows you to do is ensure that your number of direct dependents on a given deprecated library only ever goes down. And if anyone tries to violate that whitelist, that becomes an error in your graph.
Okay, that makes sense. Yeah. So that sounds like allow dependencies, right?
Yeah, exactly.
And if
so
something like that, right?
You would have like a dependency, and then you have the allowed list of people who are allowed to have it as a direct dependency. Anyone who has that dependency that is not on the whitelist flags as an error.
What we're really missing is in the CPS file the deprecated field, and then like you wouldn't have the link what you include wouldn't need extra work to figure that out.
But you need the whitelist somewhere.
You would want this config file to say, but I'm special, leave me alone.
Yeah, I'm allowed to link it.
But like, I agree with that. But like you do, there's not a good place to hang that piece of metadata, I don't think, right now, the way this is described. I guess you could put it in your CMake list.txt, but then how do you make sure everyone that consumes the thing also respects that field? I'm not clear.
I mean, yeah, but you have this configuration file now. But yes, in CPS, you could conceptually have something that says like, I'm a library, this is how you use me, I am deprecated.
Right.
And then the configuration file would just describe libraries that are allowed to ignore that deprecation.
Right.
Yeah.
Yep. I agree with that. The deprecation is a really useful workflow.
Okay. Yeah. Excellent. But I'll just land this plane and then we can keep talking about other ideas. Okay, so I'm going to summarize with my set of recommendations, right? So try to stay include what you use clean. Include what you use is hard to make it completely satisfied with your code. It will say you need to include things that you definitely don't need to include, and vice versa, right? But try to stay include what you use clean, and I think it'll get better over time. It's still being maintained and it's still getting better. So run include what you use occasionally. Consider using this miscellaneous include cleaner. Add support for link what you include, and then run it on every change. and scrutinize changes to the CMake lists that cause a change to your dependency graph. That's going to increase your visibility of your dependency graph. And then work to eliminate cyclic library dependencies if you have them and prevent them from occurring in the first place with linked with include tidy. And if you do all that, the result is a less fragile build system, increased visibility of your dependency graph, and no more unintentional cyclic dependencies. So I should mention there's a few cases that I know where link with include doesn't really work. The big one is link time polymorphism, and this might be related to what you were talking about. So that's a technique where you intentionally have one header, where the symbols in one header can be resolved by more than one library. And at the moment, that's just going to confuse link with include, because I can't map one header to 2 libraries. It's got to go to 1, right? But I think I can support that. I just haven't figured out exactly how to do it. There's an example of this in the Esri code base that I work on, but it's a really small case, and so I'm just like ignoring it for now. But I'd like to address that.
Probably, let's talk about this over time, but probably in the CPS model, you should model that as.
CPS doesn't have a good solution for this right now.
No, I mean, it could be another configuration.
Yeah. So the classic examples of this are like math libraries, BLAS,
Right.
A bunch of others. BLAS
Right. CPS probably needs a model this some way.
You're not the only person to run into this problem.
Okay.
Even if it just needs to be spelled link time polymorphism and deal with it. Like it needs to be the part of the point of CPS is you declare this kind of thing, and like it's better to say it, get it out there, and then to just let the dealer let everyone find out the hardware model.
Yeah, but
So-
the problem is it's opt-in, right? Anyone can run BLAS using the same set headers, so there's no closed set is the problem.
But you also want to warn the users that like, hey, there's 5 clauses on your link line. Hopefully that's what you wanted, but it's there. You know, like again, like the allow list might come into play or something. But
We don't hold it against you for failing here. We don't know how to
Yeah,
solve it either.
and it's not that I'm failing. I've chosen to punt
There you go.
the problem, right?
Yeah,
Like I will
think
deal
that's
with this
fair,
later.
yes.
Just like I'm the CPS stuff, right? Like I can solve problems now, and we'll make it perfect later. Okay, so another example of where this falls down is when a unit test only has tests for private header files. So in order to allow a test executable to write a test for a private header, you got to kind of like give it a backdoor access to those private headers, right? And that sort of breaks the model a little bit. And this isn't a huge problem. I don't think I'm going to fix it. I just want to like document it, because the solution for this is to write a test for the public header, which you should, right? And as long as you have that, then this backdoor is just like whatever. It's like it's fine. But anyways, it's worth knowing about when this happens a couple times on the Esri code base, and just ignore that test. That's fine. And the last one I'll mention, I'm sure there's others, but this is the only other one I know about, is when a static library intentionally exports symbols that don't have a header. And like a classic example is a testing framework that defines main for you. So you don't have to define main, you just link to this library, and main is there. But you can't declare main in a header, right? So you're not forced to include anything. So I can't really track that. So
But you just need to have a way to declare that. There's no way. You're right. There's no way to track that. You just need the user to add something to a CMake list saying, "gtest main, look what you include. I use it. Whatever you think."
So right now we don't use gtest main, but we've got something similar. You would just not pass gtest main to link what you include. Like, it's just leave that part out.
Or just get a field in the JSON file you dump that says it's one of those. Don't complain about it, and that's probably fine. Does that make sense?
Yeah.
And again, like
Yeah.
CPS probably would like have a way to say that. Yes. No, I don't have it. No, you could see in the CPS file, it's a library and it has no interfaces, and that is novel. It would not be a normal thing, and so that would be maybe a signal we could hook into to decide what to do about that.
Mm-hmm.
But yeah.
But there are analogs at the include what you use side of things where like you would include a header, but it doesn't actually define anything, but it also breaks your code if it's not included. And that can happen too, because it doesn't show up in it doesn't show up to Clang as being interesting, but it is interesting. Like for example, if you take it out, you break a different architecture that you're not currently.
X macros.
Yeah, like certain kinds of macros, that's a header that only defines things on certain architectures, and you're not currently parsing for that architecture. So it's safe to say that you're going to need a set of features that are like, no matter what you think, tool, I'm an engineer, I'm overriding you.
Escape
This one,
hatches.
yeah, this one never goes in. The one where you say this one should never go in the link line, that kind of thing's good. But there's the inverse, which is this always goes in the link line. Just trust me, it goes in the link line. That's the right thing to do. And
Okay.
you can even warn about that if you want to in different ways. But like,
Sure.
I think you're going to want that sooner or later.
Okay. Excellent. This
Yep.
is a good conversation. I like it. All right. So future goals. I want to support non-CMake build systems by using CPS. That's the big one, right? I like CMake, but not everybody uses it. And I want this tool to rule the world. I got some small things like on the public repo. I don't have a CI system. I need to do that before I start really making changes. I'd like to support link time polymorphism. I'd like to support incremental runs. Right now, I didn't talk about this at all, but it's not the fastest thing to run linked include on everything. It's way faster than a build. It's pleasant to use, but it's not quite fast enough that the people that I work with are comfortable having it as a PR gate, right? It's just not quite fast enough for that. It's close. But if I could just run on the things that have changed, then they would be a lot faster, and then I could probably get part of the faster cycle. And another thing I'm considering is being less pedantic about interface versus public scope. I fear that this might be annoying, that it's going to like say, oh, this is an interface dependency, but you've marked it as public, and you might be like, I don't care, I want it to be public. Right? So I don't know. These are like ideas that I've had.
I think it's going to be slow because you're using the full lib tooling, and at some point, maybe like far in the future, but you're probably just going to run a real preprocessor, not a full one, just up to the phase you need to, and that'll speed everything up like a lot.
So I am doing that.
Okay.
I'm just preprocessing, and I'm using the Clang dependency file system or something.
Clang scan depths or something else?
It's using the same technique that ScanDeps is using. So it is faster than actually preprocessing.
You would think that this tool exists, but shockingly it doesn't. That like they just target the headers you use directly and not indirectly.
ScanDeps is so close to what I wanted, but
It is, yeah.
but it didn't seem appropriate for ScanDeps to know about the target model, and so I felt like it had to be something else. But I definitely read a lot of that
But
code.
I think can be done. It just needs to dump the mapping of include things and what they like the files and what they include directly. You don't need it to be smart, and then your more sophisticated tool could like show up to that or something.
Yeah, there might be there's a significant overlap between ScanDeps and this tool, so there might be a future where they get combined. Okay, so the last thing I want to say is thank you for all coming. Thank you all for coming, and in particular, I'd like to thank Esri, the company that I work for, because I did all this work as part of their proprietary code base, and when I asked to release this as open source, they were very supportive, and my managers have been very supportive of all this work, and I don't think every company is like that. So thank you, and also they're funding me to come to this conference and give this talk. So like I couldn't be here without that. So thank you, and that's it.